Out of 600 people sampled, 372 had kids. Based on this, construct a 99% confidence interval for the true population proportion of people with kids. Okay, so here's the scenario. We have a population. It's much larger than the 600 people that were sampled. So some huge population, it doesn't say what population, but maybe we could assume it's in the US. And so we know it's very difficult to survey the entire country. In fact, we do this census every so many years, and that's a really costly endeavor. So most of the time when we want to answer a question about all the people in the US, we will take a sample and just take some of them, and we try to do the sampling in a way that represents the population well, and then we use that information to infer something about the real entire population. So when we're saying we want to do a confidence interval, it means that we want to estimate the true population P, the true population proportion P. We want to estimate it. We're not going to know what it truly is. We are just going to use sample information and give an estimate based on that. So the most logical thing to do, you might even be thinking it, is to take 372 and divide that by 600, and that's going to give you a percentage of 62%. So then you could say, well, a sample was taken. From that sample, we found out that 62% of people had kids in that sample. So this is not the population proportion. This is the sample proportion. Different, right? And so the sample proportion, that is a statistic because it's coming from the sample, whereas the true population proportion would be considered a parameter for all of the people. So we have our sample proportion, and we're saying, so we think the population probably has about 62% of the people have children. So that's a very fine point. It's one relatively small sample if you think about it. 600 people is not that many, especially if you're talking about thousands or millions of people. So this isn't that great of an estimation. It's not that reliable, and we have no idea how accurate it is. And things can change a lot from sample to sample, but over the long run, we'll start to see that things um, approach a central point. So what we can do, if we only have one set of sample information and we want to get a better feel for what the true population proportion is we can use probability to estimate not just one point, but an interval of possibilities for the true population proportion. And so that's what we're going to do. We're going to take our sample proportion, also known as our point estimate, okay, our point estimate, and we are going to use that to create an interval estimate. So the interval estimate is going to be represented as, well, our true population proportion P without a hat on it, because the ones with hats mean they come from samples. This one is about the true population proportion. So what we're going to do is estimate that P is between P hat, the sample proportion, and we're going to subtract a distance, okay? And we're going to call that the lower boundary. I call it LB for short. And the upper boundary, we would start at the sample proportion P hat and add a margin of error or a distance. Okay. Okay. And we are going to add and subtract that distance, and that is going to give us the lower boundary and the upper boundary of our interval estimate. Okay, so this is our interval estimate. All right, so now that we have an idea of what we're doing, how are we going to accomplish it? We know we're going to take 62% or as a decimal 0.62, and we're going to subtract a distance, and then we're going to take 0.62 and we're going to add a distance. But how do we know how much of a distance to add? Well, like I said, we're going to use probabilities under the normal curve. And so that's where we start to bring in some of the information we learned when we were dealing with finding areas under bell curves, or sometimes knowing an area and finding a boundary under the bell curve. And we're going to apply that here to figure out the distance that should be added and subtracted to find our interval estimate boundaries. All right, so with that in mind, let's take a picture of this sketch, and we're going to do a little drawing so you can visualize this a little bit better. Now, in this problem, we were told that in this example, we had a 99% confidence level given. It can be different things. 99% is for this example. And they also told us that we wanted to use the 372 and the 600 somehow. So we'll come back to that. So that's the information we have to deal with. So in our sketch here, I'm going to use that information. The 99% my confidence interval gives me my significance level alpha. The significance alpha of the confidence interval is 1 minus 0.99, and that represents the total area in the tails. So dealing in probabilities, what we're saying is we have a critical value called a z-score, and they're twins. They just have opposite signs, and they each are boundaries of a shaded area region under the curve, which represents the probability of making a type 1 error, essentially. And what we want to do is use that maximum probability of making an error and cut it in half so that it is distributed equally on both sides. So we don't want to go too high or too low, so we're going to split it up. And so we have these areas in each tail. Now the center on the normal z-score curve is always 0, meaning the center is 0 standard deviations away from itself. And when you go to the right z standard deviations, you'll be over here. And when you go to the left z standard deviations, you'll be over here. So we're going to find out how many standard deviations that is in each direction. And we're going to do that using the normal distribution, the standard normal distribution. Now you can use a z-score table, start on the inside and look up an area of 0.005 and find your z-score by working your way out, like we've practiced previously in other lessons. Or you can use the Excel function norm.inverse. So what we're going to do is find our z-score with norm.inverse. So z is going to be norm.inverse, and you always feed it a left tail area. So on the left here we have an area of 0.005. Z-scores always have a mean of 0 and a standard deviation of 1. Now, if we do this, we're going to get a negative result, and we want a positive result. So we are going to also nest it inside of another function, ABS, for absolute value. So that will get rid of the negative for us. And so that's going to represent the distance from 0. Okay? And once we have that, we'll know how many standard errors to add in each direction. Okay, and so what we're going to do is take our sample proportion, which is p hat, or x over n, and we are going to add a margin of error, and we are going to subtract a margin of error to get our upper boundary and our lower boundary. So our lower boundary and our upper boundary, that will coordinate with those z-scores, representing a number of standard errors away from the center. Now the margin of error added and subtracted onto our p hat. How would that look? Let's see. Okay, so in this case, we have the critical value, as I said, absolute value norm dot inverse with an area of 0.005, a mean of 0 and a standard deviation of 1, close my absolute value function, and I have my critical value of 2.576. So what we're going to do is we're going to take our sample proportion of 62% or 0.62 as a decimal, and we are going to add on 2.5, a little more than 2.5 standard deviations. And when we're talking about a sampling distribution, like where you're not just talking about individual values selected, but an entire sample selected. Remember, we used the central limit theorem when we had something called a standard error. Well, this is similar. We're going to use the square root of p hat q hat over n to represent our standard error for proportions. So these other two formulas were for calculating a margin of error when you're estimating a mean, a population mean. Here we're talking about proportion, so we're using a different formula. So we're going to use this. This will calculate our margin of error E. Okay, so we're going to take whatever that standard error is, and so we know we're going to take 2.576 standard errors. And what is the standard error? It's p hat q hat over n and take the square root. So we need to figure out what is p hat, what is q hat, and what is n. N is easy, right? We saw up here that there was a sample size of 600. I'm going to put that in, 600. P hat is the proportion of successes. Now notice that they counted 372 people having kids out of the 600. So the proportion is 372, right? 372 out of 600. Okay, that's where we got our 0.62. Now Q hat represents the proportion who don't have kids, or the not successes that we count. So 1 minus 0.62. All right, so we now have our bits and pieces. We can use those to calculate the standard error, also thought of as a standard deviation. And we are going to take the square root SQRT times a square root of p hat times q hat divided by n. All right, so there's our standard error, which is about 2%. So we're going to add 2% how many times? 2.576 times. So what do? We multiply them. That's literally what we mean. This number, this many times. Multiply them together. There is your margin of error. Your margin of error is going to be added onto your point estimate. What was the point estimate again? Oh yeah, it was the 0.62 that came from dividing the number of successes, which we commonly think of as x, divided by n, the sample size. So 0.62, add and subtract that margin of error. Okay, here's our margin of error. All I did was copy it down. And the parameter that we are estimating, again, is P without a hat, meaning the true population proportion. So we estimate with 99% confidence that the true population proportion is somewhere between P hat minus E and P hat plus E. Okay, the point estimate minus the margin of error, and the point estimate plus the margin of error. And that's it. That's how we get our answers. And these are rounded to 3 decimal places. I think that's what was requested here. Yes, okay. So you can change the rounding and the format on all of these as you would like or as necessary, depending on the instructions of the problem. You just right click on the cell. You can go to Format Cells. You can choose number and change your decimal places. You can make it a percentage and do the same. Okay, so there's lots of options there, but that's the gist. And these are in the form that we wanted them in. So we are all done with this problem, and I hope that helped. Bye.